All right, so now that we have determined the stoichiometry for our reactions, we can go ahead and use that to determine the number of moles we're going to have of each substance after the reaction and before the reaction, and then also use some data, the heat of formation for each of these, to determine the temperature of the flame. So basically the way we're going to be doing this is we're going to look at the enthalpy coming in to the reaction and the enthalpy that's going to be leaving, and using that difference to determine the temperature of the flame. So the first thing we're going to do is take a look at some properties for one of the substances we have here. We have methane, and we're going to be using this for methane, propane, ethane, oxygen, nitrogen, and then also our carbon dioxide and our water. And we have the heat of formation, which is the main thing we're going to be using, and that's in joules per kmol. And the way we're looking at this, again, is going to be the enthalpy that's coming in the form of our natural gas and our air, and then the enthalpy that's going to be leaving. And then we're going to be using that difference in enthalpy to determine the temperature of the flame. So we can go ahead and bring in this data for all of our substances, and we're just going to make an array of all of our substances. We have methane, ethane, propane, actually propane is N-propane, carbon dioxide, I believe, and then let me just scroll through here and double check. We have carbon dioxide, we're going to also have nitrogen, and we're going to have water. Okay. Carbon dioxide is good. Water, oxygen, and actually I'm going to move oxygen by our natural gas constituents. Sorry for the alarm going off in the background. And then we also have nitrogen. So I'm going to go ahead and look up this error real quick, and I'll be right back. My error was I simply forgot some parentheses here. All right, we're good now. And then we're interested in the heat of formation of each of these. So I'm going to go ahead and use that. So again, this is the heat of formation of our ideal gas. We have a bunch of other functions that we could use, but for now we're just going to use this. And then if we go ahead and run that, these are heat of formations for each of these, methane, ethane, propane, and then we have oxygen, we have carbon dioxide, water, and then we have nitrogen. All right, so some interesting notes about this. These two are 0. This is oxygen and nitrogen. And actually, I'm going to go ahead and move those together just to make it a little easier to work with. But the reason those are 0 is because oxygen and nitrogen, O2 and N2, are in their natural state. So they're basically at the simplest form, or the form that they want to be in. So there's no enthalpy of formation. And then from here, we're going to have to determine an equation for our change in enthalpy, and then also our change in temperature. And then we're going to be using our stoichiometry as well as these values for the heat of formation to determine the total change in enthalpy, and then use that to determine the change in temperature. So now that we have our enthalpies of formation, we can go ahead and find the equation that we're going to be using those in to determine the temperature of the flame. And forgive me if this is a bit clunky. I'm trying to split screen on a drawing tablet here, but we're going to give it a go. So usually when we look at things, we think of, especially when we're looking at things with a very small temperature range, we think of our heat capacity as a constant. But when we're looking at really broad temperature ranges like we are here, where we have something coming in at roughly room temperature and then leaving as a flame, obviously there's going to be a really big range of temperatures there. So a better way to look at this for now is that the change in enthalpy is going to be equal to the change in enthalpy with respect to temperature at a specific pressure times the change in temperature. And obviously these two just cancel out. And then we think of this term here when the temperature change is really small, or there is no temperature change. Since these two are going to be equal, it's going to be roughly equal to the change in enthalpy. So we don't really worry about this, but when we have this broad range of temperatures, we do have to factor this in, and you'll see why in just a second. But then also, if we weren't looking at an ideal gas, we'd have another term where we have the change in enthalpy with respect to pressure at a specific temperature times our change in pressure. But we don't need to worry about any of that because we are looking at an ideal gas. So another way to write this is delta H is going to be equal to Cp times the change in temperature. And that's pretty easy to see. We're basically just turning these D's into deltas. And this will be equal to our change in enthalpy. And then from there, we're going to be using an equation that we can find in this ChemCAD. Let's just look at ethane from now. And I'm jumping around a bit. See if I can get this to open. There we go. I think it'd be easier tapping with a pen than clicking, but it's not. Okay, we're going to use the cursor. So if we scroll down a bit, where is it? I think I passed it. There we go. Okay, the ideal gas heat capacity. We're looking at these values here. There's 5 values. You can't see them all. Let's see if I can get it. Close enough. You can see 4 of them. But this is going to correspond to A, B, C, D, and then over here, E. And an equation we're going to take a look at in a second. And basically, you use this equation to determine the heat capacity over time as the temperature is changing. So hopping back over to our notes, we can rewrite this again. And I might have to bring back the drawing tool. We can say that the integral, as the enthalpy changes from enthalpy 1 to enthalpy 2 of our change in enthalpy is going to be equal to our change in heat capacity. That should have been a T. Try that one more time. Our heat capacity, change in temperature, or the integral of our heat capacity in respect to our change in temperature. So if we go back over here, and we take a look at this ideal gas heat capacity, it says equation number 107. So I'm going to go ahead and pull that up. I'm going to pull it up on my screen that you cannot see, and then I'll move it down. So this is ChemCAD equation 107. It looks really ugly for some reason, but I guess we're just going to have to live with it. It looks like they're using the weird new Microsoft default font. Oh, there we go. It's a bit of a pain moving between this drawing tablet and my regular screen here. But again, we're looking at equation 107. Don't know why it's grayed out like that either. I think you should be able to see that. But we're looking at equation 107 here. Right here. And this is going to be our equation for the heat capacity. So this is going to be the equation that we're integrating. And once again, that A, B, C, and then D, E are going to be those numbers that we saw before in our CHE tools. Okay, so now that we have our equation, we need to go ahead and integrate it. Sorry, I'm waving my mouse around, but you can't actually see it. We need to go ahead and integrate it to get this term here. And then from there, all we have to do is evaluate it between two temperatures, and that's going to be equal to our change in enthalpy. So I'm going to pull up Wolfram alpha, and I'll just do the first. I'll just do the first one, and then from there I'll tell you what the second one is. So we want to integrate. We can do this one in our heads pretty easily. It's just going to be A times T. But then we have this term here, and then we're also got, again, I'm waving my mouse here. We can do this one in our heads, and then really we only have to integrate this term here, and then also this term here, because they're going to be multiplied by a constant. We can move the constant outside. So that'll clean things up quite a bit. So we're going to have the integral. And you know what? I'm going to do things slightly differently than I originally planned to in an effort to make it slightly easier on me later on. And you will see why. But I'm going to go ahead and integrate this whole thing. So we have A plus B. I'm looking up here because I can see it in OBS and it's just easier. And we have C plus T divided by, well, we are going to have to put that in parentheses, C plus T divided by sinh, which is just a hyperbolic sign, sinh of C divided by T. All right, and then that whole term is going to be squared. And then we're also going to have plus, and then I'm going to go ahead and copy this over because we only have to change the variables. We're going to have D and then E plus T and then E over T. And then this is going to be cosh. And then we are going to be integrating this whole thing with respect to T. So let's go ahead and run that, see what it spits out. Wolfram alpha is taking its time today. Well, I will cut out here and then come back once Wolfram alpha has caught up. and if it doesn't, I'm just going to go ahead and write it down myself. So Wolfram Alpha was being really weird, and I ended up having to do it on my phone, but I went ahead and wrote it down. One thing to note is that I wrote this as an indefinite integral. We will be evaluating it from one temperature to another, but I just wrote it this way now to save space, honestly. Really terrible integral here. So from here, we just need to put this in Python, and if you'll give me a second, instead of cutting out here, I'm going to switch what I am showing on my screen here. All right, and then from there, I can go ahead and move my Python. Wow, that went oddly smoothly. Usually it doesn't work quite that way. So the reason I wanted to write this all out, and I'm going to be referencing off my notes that I took down here, but the reason I wrote that all out is just because I think once I do this next step, I'm going to try, and I've never tried it before, so it might go terribly. I think it'll just be a little bit easier to manage. Sorry, I had a weird bit of issue with OBS, but I got that figured out. So now I'm going to go ahead and define our A, B, C, D, and E, and I'm just doing this way to clean things up a little bit. And they're going to be equal to P. Got to remember the, oh, there we go. CP, IGA, B, C, D, E. IGB, P dot, CP, IGC, P dot, CP, IGD. And technically this isn't really going to save us any lines of code, but I do think it makes it a little bit easier to work with, and especially like going back to review this, it will be a lot easier to look at our later functions and not really have to worry about what each of these things are. So let's go ahead and run that. All right, and so our next step is going to be making a function that is going to be our formula that we came up with down below. You can't see it, but our AT plus B, et cetera, our integral of equation 1 of 7. So I will define our function, and we're going to call it integral of CP, and then our input is going to be temperature. And we're going to have it return A times T plus B times C. And we wrote it down as tanh, but I'm going to write it as cotangent. And then these are technically in parentheses, so we'll leave it like that just to make it a bit easier to read. But C times our coth, our hyperbolic cotangent of C divided by T. And then minus our D times our E tanh of our E divided by T. And then make sure the parentheses are good. Go ahead and run that. So yeah, really, we didn't have to do this, but it did save us a little bit of space down here, made it look a lot cleaner, I think, instead of having to write each of these out. So now that we have our equation for our integral, we can go ahead and sum up our enthalpies. So we're going to have our enthalpies of formation, our enthalpy at, or sorry, the change in enthalpy from our temperature initial to our final temperature. And so the way that we're going to do this, we're going to use a final temperature of 25 degrees Celsius or 298.15 Kelvin. And then we'll just write this out in a way that's easy to understand. So we want to return our integral, or actually let's go ahead and start out with our enthalpies of formation. Plus our integral Cp at our temperature, and then we'll specify the temperature later. Sorry, a bit tired. And then we're just going to subtract our starting integral, or our integral taken at our starting temperature, which is going to be 298.15 Kelvin. And then from there, we have to determine the number of moles we're going to have of each of our substances. And then we're just going to do a little bit of math, and it should give us the change in temperature.